Take it away.
Thanks, Helen. So as Helen said, I'll be talking about rare earths in phosphate-bearing sediments in Queensland. Before I get started, I'd just like to acknowledge that I had some help. So we had a lot of help from industry in providing samples during COVID while we were not able to get out in the field ourselves. We also had a lot of the benefit, a lot of their context and a lot of their experience in helping me understand and interpret the results that we were getting throughout the year. And also I'd like to acknowledge my co-worker, Michaela, for really kicking off this project before I arrived. So as Helen and Vlad have done a good job introducing the context of the work that we're doing, I'll just kick straight off into it. This project is part of this new NEMI initiative, so it kicked off earlier this year. It's understanding the rare earth element endowment of these sediments called phosphorites. So they're a marine sedimentary rock, by definition contain more than 50% or more phosphate minerals. They often contain in excess of 30% P2 phosphate. They're the main source of the world's phosphorus for fertilisers at the moment. And the reason why we're looking at them is because they can contain rare earth elements. So Ross had a similar slide, but just to my definition of rare earth elements, according to, I think, everyone but Europe, is yttrium and the lanthanides. And just a point to note about these, and Vlad touched on this too, only a handful of these are actually worth anything at the moment. And it's important that if we're looking at these things realistically, that we understand the proportions of the different rare earths, because we're not going to find a neodymium mine. They're all going to be together. They're all chemically quite similar, and they're all energetically quite difficult to pull apart. So understanding what the different proportions are, and also trying to find associations with already economic mineralisation of other sorts is quite favourable. So with that in mind, this is just a bit of a teaser of what they look like. Vlad's already shown you this. This is the light rare earth elements on the x-axis versus the heavy rare earth elements. And the blues and green are Georgina Basin phosphorites. Not all of them that we've analysed, but they sort of follow that general trend, and this sort of covers the lower and upper ends. For context, I've included other rare earth element sources that we've all been sort of thinking about, and some of us have been talking about today. So we've got some peralkaline volcanics from Toongi in New South Wales in that sort of peach colour. We've got a carbonatite from Nolan's Bore, and sort of for context, what their mine sort of sits up here somewhere up in this sort of top. Well, where's the? I've got to go over. Here we go. Up here. So this is sort of this is where the head grades would sit for something that they'd mine, for example. So as far as the phosphorites go, they start to stack up really well. But interestingly, the red dots are ion absorption clays. So the world's dominant source of heavy rare earths, which are supply of which is controlled by China at the moment. The phosphorites actually stack up pretty well next to those. But if we just take a step back for a moment, this is just an overview of what I'm talking about. So I'm talking about the Georgina Basin. This is dominantly actually in the Northern Territory, but we have the eastern margin here and sort of up against the western part of the Mount Isa inlier. And you can see that here more broadly, where the grey is the Mount Isa, and this hash stuff is the current mapped extent of the Georgina Basin. But I think more instinctively for me, the sort of sea base that underlines it, that sort of that depth image, you can sort of see it deepening out to the west, and that's the Georgina Basin eastern margin there. All the red dots are known phosphorite occurrences that occur up and down in these things, and they occurred over sort of several million years in the mid-Cambrian through, I think it was 5 marine transgressions. And these differed slightly based on sort of the local structures that define the sort of the north and the south and the southeast. So you had the Andilla Sub Basin in the north, the Oban Sub Basin in the sort of southwest, and the Burke River structural belt down there near Phosphate Hill. Just to let you know where you are in the stratigraphy, we've got this sort of middle Cambrian sequence of sediments deposited during several marine transgressions. Within those, your phosphorites sit as either discrete members, which we see down south in the Monastery Creek or the Simpson Creek phosphorite members, or otherwise as sort of layers within the sort of phosphatic siltstones, some siliceous assemblages as well, some mudstones, and then underlying those are silts and limestones, and interbedded through all of these are cherts. So historically, from a phosphate perspective, these things have been grouped into different domains. Once again, this sort of calls back to the time of their deposition. the control of the sub-basins in their sort of shelf morphology where these things were sitting. So this was the sort of the amount of time these things were sitting on the ocean floor, the degree of a shelf or a carbonate platform being built or not, and different things like that. And as a result, we actually see quite significant variations in the mineralogy, the morphology of these phosphorites. And two examples here are a sort of paletal phosphorite where you can actually see individual grains. It feels very much like an unconsolidated sort of sand, versus these very, very low energy mudstone phosphorites where you can see brachiopod fossils and things like that. So in terms of like those differences in their genesis, what we see is we see a difference in the overall phosphate grades, the associated chemistry, so iron, silica, and all those sorts of things, and these sort of hearken to differences in their formation or lead people to think about how they might have formed. Historically, the rare earth elements have really only been studied to understand their sort of genetic or digenetic behaviours, not dissimilar to how rare earths have traditionally been used to understand volcanic systems, for example. But we know that they're there, and it's generally understood that they sit in the primary phosphate-bearing mineral. It's a carbonate fluorapatite mineral. Sort of a colloquial term is francolite, which I prefer to say because it's easier, so I'll stick with that. The rare earths sort of sit in the calcium spot in that mineral. There's also some other minerals that I'll sort of go into a bit later that contain rare earths in these systems, and these are often secondary minerals such as crandallite and xenotime, and there's also some clays. So the different phosphorites, as we were sort of going into this study, we wanted to get a feel for how these things might behave and do they vary over time, and the literature suggests they very much do. These are a couple of examples this isn't chondrite normalized, this is sort of shale normalized, so the normalization factors are quite a bit higher. These are sort of would be used as a proxy for what's going on in the crust. So anything above 1 in this case would be enriched relative to crust, you could say. And what we've got here is we've got some literature values for different phosphorites around the world, and you can see two main things. One, they vary in rare earth element concentrations by a couple of orders of magnitude. There's also some differences in the relative abundances of the different rare earths relative to each other. And so existing work from the USGS especially has identified that these things are often laterally continuous, not just in terms of their existence, but also their rare earth element chemistry. So of a given layer of these things, they're quite homogeneous in terms of rare earth elements, but over time, they vary quite wildly. So just to sort of contextualize the results I'm going to show, some of the proposed variabilities in the rare earths and the functions for those. So the depositional environment initially. So one of the favoured things here is looking at differences in seawater chemistry over time, not just in the amount of rare earths, but the redox and the ability of the rare earths to be scavenged out of the seawater. Localized upwelling, so it could be that there's some favourable. So the localized upwelling is one of the things that they think contributes to the phosphate enrichment due to the influx of organic matter. So that might also change the conditions and prompt precipitation and things like that. The other thing about these phosphorites is that they're very condensed sections. So over a long period of time, not much sediment accumulates. So it means that these things accumulate slowly, spend a lot of time at the seawater sediment interface where a lot of chemistry can take place. And the other thing is just depth as well. So that's the sort of the primary factors that may control it. But the formation of the francolite itself actually happens during diagenesis. So you take carbonate minerals, and you also take these phosphate-rich organics, and you react them during diagenesis to form your carbonate fluorapatite. And some people suggest that the pore-water interaction at this stage may introduce rare earths. And finally, and what I'll go into a little bit is the effect of weathering on these things in mobilising and potentially enriching rare earths. So our aims are quite simple, looking at the phosphorite occurrences on the eastern margin of the Georgina Basin, just to characterise a rare earth element endowment. So this is where the companies came in being very generous in providing samples, especially during COVID where I couldn't get them myself. And so we characterised the rare earth element endowment of several of these, And then the sort of next stage is to try and identify factors that are linked to rare earth element enrichment. So stratigraphic position, so the age of deposition, harkening back to the seawater chemistry perhaps, or a geographic position, or as I said, weathering. So what we've done is we've taken samples from all the locations shown on this map. So we've got some BMR drilling down near Duchess. We've got most of the main deposits, as Vlad pointed out. We're still missing some from the north. We've got a variation of RC drill core, diamond drill core, pulps, and grab samples from pits. And we've done a combination of bulk and in situ analysis to really try and pin the chemistry to the mineralogy and try and infer some processes based on that. And so, as I showed before, and as Vlad showed, these things have turned out pretty well in terms of overall rare earth element endowment in some aspects, but we can also see that some of them aren't that enriched either. And as you've now seen this twice, I'll quickly switch on to the next one. This is another spidergram. Once again, we've got the peralkaline volcanics from Toongi. We've got the Nolan's Bore carbonatite, and these are normalized rare earth elements patterns showing the various distributions of light versus heavies. A couple of things to note here, that the carbonatites are famously light rare earth enriched a lot of the time, and we can see that ours are looking pretty heavy enriched, which is nice. But you can also see that spidergram's a pretty chunky boy. So we've got quite a lot of variation in rare earth element concentrations there. And the way that looks spatially distributed across the basin is I've got the dots are somewhat eyeballed, but the concentrations are legit. We've got some what I'm calling fresh, so these things are weathered, but my definition between fresh and weathered moving on is the difference between whether or not you've got secondary phosphates forming due to advanced chemical weathering. Because the rare earths are typically reasonably immobile, I'm assuming that even with the oxidized ones, the sort of primary francolite mineral that I'm seeing in there represents the primary rare earth element endowment. So the first thing to note, obviously, is that from north to south, you're seeing quite an increase in the sort of fresh rare earth element endowment of these phosphorites. The second thing to note is that across the basin, irrespective of where you are, weathering appears to play a reasonable role in upgrading these things quite significantly in some places. So you can see Ardmore there is up to a couple of thousand, maybe 2,500 ppm. But when you weather them, they can get over 1.5% total rare earths. So that's the first thing. And you can see, secondly here, this is a depth profile with concentration across the y-axis. So here we go. So you've got total rare earths across the y-axis. You've got depth down here. So these are pulp samples through some RC drilling. And I've done quantitative XRD on them to measure the amount of crandallite. And you can see that there's this sort of secondary mineralization that enriches in rare earths. So we'll go into that a little bit now. So this is the same profile, but I've got aluminium and phosphorus there. So you can see that this main chunk here is a dominant phosphorite layer. Above that, we've seen some aluminium enrichment. We've also seen some rare earth element enrichment. What we typically see is that the weathering fluids react with the phosphorite and mobilize certain things, and immobile elements stick around and enrich. So those are the rare earths in this case, and your aluminium. So you get a hydrated aluminium enriched phosphate that's also enriched in rare earths. When you continue to do that, so up here I've shown total rare earths together in blue. If you look here, I've divided them up into light versus heavy. So the lights are in green, the heavies are in grey. And what you can see here is that in the top section, this slight bump here is attributed to that sort of subtle weathering in the crandallite formation, and the lights and the heavies generally follow themselves down section. However, when you get more advanced weathering, and I'm inferring that it's more advanced based on other observations, you actually see a breakdown, I think, of the crandallite, and the crandallite itself then begins to react to form other secondary or even tertiary minerals. And in this case, I've identified xenotime in a sedimentary setting. So just as a quick like 8-bit sort of style picture to show you what I mean. So this is your fresh phosphorite. I've got a shale layer over the top, and I've got some diagenetic or some syngenetic pyrites in there. And as you begin to weather that, you start reacting the phosphate, the primary phosphate mineral francolite, to form your crandallite. the rare earths at this stage are immobile, so they're being enriched in those sections. As you continue, you break down the crandallite even further and you start forming these xenotimes. So that's suggesting that you're actually starting to mobilise the rare earths at this stage and partitioning the lights from the heavies. Another thing to note, just for future context, is that we do see at the deposit scale these processes not just happening as weathering fronts, but increased to increase depths and increase volumes when you've got localised structures that are allowing water to get down into these sections. So what we did is we took some chunks of this phosphorite. We measured it at UQ using sort of a SEM mapping technique, MLA, to get a grasp of what the mineralogy was doing. And what we've got is we've basically got in these weathered sections a crandallite-rich assemblage, and in some cases you see the xenotime and even monazite little pieces in here, only in discrete layers though. This is a couple of mil little aggregate of fine-grained matrix. And then what we did is we chucked it on a micro XRF and mapped it. And what you can see here is you can see this distribution difference in the lights versus the heavies. So I've got cerium and neodymium here enriched in the crandallite-rich layers, and you've got your gadolinium, ytterbium, and yttrium enriched in the xenotime-rich layers. So this is seeing what we're seeing at the drill core scale on a micro scale. And so although this work has been really exciting, it's not particularly new. This is something that was released back in 2011 by Crucible, and this is looking at a sort of structurally controlled yttrium resource at Corella, which, as you can see, just sits very, very close to Phosphate Hill here. Ardmore's up here, and what they showed is that you have yttrium enrichment at the top of your phosphorite, where you've got it in contact with the overlying shale, and also in these discrete structurally controlled sections as well. And so this is very consistent with what we've been seeing in our phosphorite study, and how that actually looks. So this is from that public release. This is their high grade yttrium sort of inferred resource here, and this is their highest spot grades that they reported for those particular minerals, and how that actually stacks up against our sort of chunky spidergram, of which I've sort of pulled out the rough bracketing of Ardmore, Phosphate Hill, and Paradise North and South for context. So just to sort of finish up, some people are already looking at this. So in China, they're already looking at rare earth element extraction directly from phosphorites by acid leach, and the feed grades are talking about a 0.1 to 0.5% total rare earths, and that's well within the sort of fresh phosphorite compositions we're seeing certainly in the southeast. In Norway, they're actually doing it from apatite at a fertilizer plant. So they're getting the rare earths out first and then actually going on to make a fertilizer concentrate. And their feedstock is only about 0.3. So that's right up there with some of some of this stuff fresh out of the ground is that. And that's not the weathered stuff. So these are, in context, actually reasonably promising. The weathered stuff is high in aluminium, as I said before, because it is incompatible during weathering, or immobile in weathering, I should say, and that's a real problem for the fertilizer manufacturer. So looking at the weathered stuff as a potential sort of combination of extraction may not be viable because it makes their solutions viscous, and it reduces the sort of bioavailability of the phosphate in the final product. But as a potential, I mean, consequently, that stuff is then thrown away as waste at the moment. So if you look at this as a potential sort of use of a waste product, then you know it's really high grade. Some of this stuff is exceeding 1%. So that's actually pretty exciting. And so just to take home messages, so there's significant regional variation in the primary rare earth endowment of these phosphorites, as you can see. You know, if I was looking for this stuff, I'd probably stick down to the southwest there. Evidence for weathering or low temperature alteration is linked to the enrichment of rare earths across the board. So maybe some of the highly weathered stuff further to the north may still be viable to be taken as waste in an active phosphate operation, and the degree of weathering and rare earth enrichment may be influenced by the localized structures, and also, as I sort of showed in that little simple model, the composition of overlying sediments. So if we've got, you know, the mobility of rare earths is strongly influenced by pH. So if you have an acidifying assemblage over the top of these at the time of weathering, then that actually may be crucial. All right, so that's me. Any questions?
Any questions? Oh, look, Peter.
I know with Crucible's little deposit south of Duchess, they reported lead endowment, and I think it might have been the ballpark of about 10 million tonnes at 1%. I know that with the Moorstone lead occurrence in Cambrian sediments west of Lady Annie, there's also substantial lead anomalism that was drill tested by CRA perhaps 30 years ago. I didn't know whether you'd looked at any of the other base metals or looked at the lead itself. I mean, one of the questions there is, what's the origin of the lead? Is it, you know, is it part of an MVT style Cambrian system, or is it actually from deeper Proterozoic sources?
It'd be interesting.
Plumbing. Anyway, it's just a question.
Yeah, it's good to know.
Don't know if you happen to come across some lead, maybe you should have a look at it.
Definitely will. Thank you.
Paul.
Thanks, Matt. Hey, what do you link that trend to the southwest with? Is trend in phosphor or trend in rare earth? Is it sedimentological, or is it basement geology? Or
I think it's that. I have no real solid basis for this. I've spoken to this with my colleague Michaela, and yeah, I think it's weathering off. We both think actually it's what's weathering off the Mount Isa inlier in the Cambrian that might be dictating that. That would be my first sort of investigation direction from that.
so sedimentological.
Yeah. So a primary, sedimentological, but what's weathering off. So as opposed to what's happening in the sea at the time, probably more what's being contributed locally on a regional scale, but locally in a marine sense. So that's my guess.
And where does the phosphor come from? Is it poop?
Yeah, well, I believe it's small little bits of biota being upwelled is a generally accepted model. But a bit of poo. Yeah, a bit of poo's not going to go astray in that model. Yeah.
We had to go there, didn't we?
He started it. Thanks, Paul.